Um, Thank you, Sangeeta, for talking at our event. Sangeeta Chowdhary is a PhD student at Rutgers University, and her advisor is Professor Santosh Nagarakate. I hope I got that right, who's also here with us today. Her work focuses on developing new compiler techniques to ease debugging of numerical applications. Before joining the PhD program at Rutgers, Sangeeta worked at Samsung R&D Center in Bangalore, India, as a software engineer where she designed networking interfaces for mobile phones. Thanks for talking at our event, Sangeeta. You can take it away.
Thank you. Thank you, Anupma. So I'll start. Hello, everyone. I'm Sangeeta Chowdhary, and I'm a PhD student at Rutgers University. And today I'm going to talk about my thesis work to detect and debug numerical errors in FP applications. So they are infinite real numbers, and they are approximated in computer systems for performance reason. And floating point is one such approximation, which is used widely everywhere, from artificial intelligence, scientific computing, weather simulation, gaming, and list goes on. Rounding errors in floating point arithmetic are often negligible, but sometimes they can result in catastrophic incidents. For example, recently a driverless race car went straight into a wall due to a floating point exception. In this incident, the steering control signal resulted in a neg, and subsequently the steering locked to the maximum value to the right. So let me start by giving you some background on floating point representation. So with real arithmetic, we would expect the output of this program to be true, but floating point arithmetic is an approximation of real arithmetic. And that's why a simple program like this can result in unexpected output. So now let's try to understand what is going on under the hood. So floating point representation stores a real number in a fixed bit width. In a 32-bit representation, 1 bit is used to store the sign of the number, 8 bits are used to store the exponent, and 23 bits are used to store the fractional or the mantissa part. So now coming back to our example where we try to add two decimal numbers, 0.1 and 0.2, and let's see how 0.1 is stored in 32-bit FP representation. So first we will convert the decimal 0.1 to binary, and we will get a non-terminating binary representation. It is similar to decimal numbers where we get non-terminating. Similarly, in binary, we get non-terminating numbers. And second step is to convert it to the normalized representation, which is to move the decimal point to have a leading one. And since we have to move the decimal point to the right by 4 position, we'll get exponent as -4. So we'll store the exponent -4 in the exponent field. Here we are assuming non-biased representation for simplicity. And we'll store the fractional part or the mantissa part as you can, but the mantissa part, as you can notice, it's a non-terminating fractional part. So we have to fit it in 23 bits, and that's why we need to round that. And when we convert this representation back to decimal, we'll get some number close to 0.1, which is not exactly 0.1. So similarly, we'll store 0.2, but the actual value being stored is some value close to 0.2. And what we are ended up is comparing two different representations of 0.3. And hence this program would result, this condition would turn out to be false, and a program would return false output. So the moral of the story is that rounding errors for primitive FP floating point instruction is most of the time negligible. But in some cases, rounding errors become significant due to accumulation or catastrophic cancellation, leading to wrong output, branch flips, slow convergence, etc. So now let's take a simple example where we are trying to find a number of roots for a quadratic equation. So we compute the determinant of this equation, which is b square minus 4ac. And if it is greater than 0, then we have two distinct real roots. If it is equal to 0, then we have one real root. And if it is less than 0, then we do not have any real root. And if we write this in a program, so we will have this program. And now suppose this program returns a wrong number of roots for some input in comparison to the real arithmetic. So the one way to debug this program is to rewrite the program with higher precision and compare the output. So here, higher precision, I'm saying higher precision because we are getting numerical errors because of the loss of precision. And high precision works as the oracle, which we can compare and find the error. But there are two main issues with this approach. First, manually rewriting the program in higher precision requires a lot of effort. And second, rewriting the program would not help us to detect errors at the granularity of the instruction. So we want to automatically rewrite the program in higher precision, and we need to do a fine-grained comparison to detect errors at the level of instruction. And this is where we can, so inlining this high precision code with floating point instruction, this is what we call as inline shadow execution. So our goal is to detect numerical errors with floating point applications. And to achieve this goal, we shadow every floating point computation with real numbers. The computation with real numbers is the ground truth, and to compare, and we can compare and detect numerical errors. So using compiler instrumentation and careful design of metadata help us to reduce the memory overheads in comparison to prior approaches. Along with that, we also want our developers to identify the root cause of the numerical errors. And to achieve this goal, we provide a directed acyclic graph of instructions or a slice of program to show the error propagation. And the key contribution is how do we provide the slice of program while maintaining a constant amount of metadata with each memory location. So now let me demonstrate how FP sanitizer works with this running example. So to enable inline shadow execution automatically, we transform the program at compile time. And for every floating point variable, we store the metadata in shadow memory. And since we are instrumenting at compile time, that means FP variables are either resident in registers or they are either stored in memory. That means we need to track and store metadata for variables in registers and in memory. So now the question is, where should we store the metadata for variables in register and in memory? So for variables in register, we store metadata in the program stack itself. We reclaim the metadata once the stack frame is deallocated. We provide the unique identifier to map temporaries at compile time and use this to map the metadata in program stack for variables in registers. And for variables in memory, we store metadata in shadow memory, and we use memory address to map these metadata in a hash map. So now the question is, what do we store in the metadata? So we need to store the real value for the FP computation. So we need to store the real value for every FP computation. The real value is the high precision value, which is the ground truth to compute the numerical error. We also store the computed value in the metadata, which enables selective shadow execution. For example, if we do not have a high precision value available in metadata, we reset it with a high precision value. Such an example is a call to an external library. And for this function call, we will not have a high precision value. And in such cases, we reset the metadata with the computed value. And we store the pointer to the metadata of both operands. And this helps us to generate the acyclic graph of the instruction for root cause analysis. Now for the store instruction, we store the real value, FP value, and the pointer to the temporary that has been written to the memory. The storing pointer to the temporary avoid unnecessary replication of metadata and help us to trace the provenance of numerical errors within the memory. But what if the stack frame is deallocated? Then this pointer to the temporary and shadow memory metadata will be a dangling pointer. And that means we need to ensure the temporal safety of all pointers in the metadata space. And we use the idea of lock and key from sets proposed by Nagarkate et al. When the stack frame is allocated, we provide a new lock and key. The lock and key will match as long as the stack frame is valid. The pointer accessing a stack frame inherits its lock and key. When the stack frame is deallocated, the stack associated with the stack frame is invalidated. Hence, lock and key for the pointer accessing the stack frame won't match, ensuring the temporal safety of all pointers. Now, let me walk you through the simple example step by step. So for variables in memory, we store the metadata in shadow memory. And in metadata, I'm just showing the real value, FP value, and the pointer to the temporary for simplicity. For variables in register, we store metadata in the program stack. So the first thing in this program I'm doing is dereferencing a pointer, PTR1. So in the shadow execution, I'm going to access shadow memory associated with PTR1 and load the real and a floating point computed value in the metadata space from shadow memory to foo's stack frame. Now to initialize the pointer to the metadata of A's operand, I need to access T28, which is the pointer to the temporary in the stack frame. So if this pointer, if it is valid, then we copy the metadata associated with the operands of T28. Otherwise, we initialize operands metadata to null. So in this case, it is invalid since we do not have an entry for T28 in the stack frame. And that's why the pointer to the metadata of A's operand is set to null. Similarly, we load metadata for B from PTR2 and metadata for C from PTR3. And now I'm calling a function root count. So in root count, we are creating a new variable T1. In shadow execution, we create metadata for T1 in root count stack frame. We retrieve the real value from B for B from shadow memory and compute using real value and store it in T1's metadata. So we store the FP value pointers to the T1's operands metadata, which is B in this case. We do the same thing for T2, T3, and T4. So after computing T4, we notice that T4 has high rounding error. And as you can notice, T4's computed value differs from T4's real value. But looking at just T4, we do not know what is the root cause of the error. So in T4, the previous rounding error is being magnified. And to diagnose the root cause of the error, we can traverse back following the pointers to the operands metadata and investigate how the error was propagated. So the first thing we have noticed is that subtraction operation at T4 has error of 62 bits. And from T4, we access the T1 and T3's metadata and notice that operands have the error of 43 bits. We recursively traverse each node and construct the entire tag. So we can now figure out that T1 and T3 have error due to loss of precision, and it is magnified in T4 due to catastrophic cancellation. So now we return from the root count function, and root count stack frame is deallocated. At this point, T5 metadata is storing a dangling pointer to T1 and T3's metadata. So that means that we need to check temporal safety. So by checking temporal safety metadata, we can know it is unsafe to access these pointers. Hence, at this point, we won't be able to produce the DAG of instructions, and the user has to put a breakpoint just before this execution point to produce the DAG. So this design of storing the constant amount of metadata in the program stack and following it to get the DAG makes FP Sanitizer scalable with long-running applications. So now let me quickly discuss the overheads we have in comparison to uninstrumented application. So the average overhead of shadow execution compared to the hardware floating point type is 110x. So which is good in comparison to the state of the art, but it's not great. So the next line of work is to perform parallel shadow execution to reduce these overheads. So with FP Sanitizer, we have performed inline shadow execution to detect numerical errors comprehensively. Now our goal is to run shadow execution in parallel to reduce the overheads of inline shadow execution. To get scalable speedups, we need to split the shadow execution in various fragments, but we do not know at what points we should split the shadow execution. So that's where we let the user mark the code regions for shadow execution. And based on user annotations, our compiler automatically generates shadow tasks. However, with our approach, we are trying to extract parallelism from a sequential program. And that means we need to start a shadow task from an arbitrary point. And we have to provide an appropriate state to enable that. And our key insight is to use original floating point values to reset the state. Hence, shadow tasks are dependent on the original program for the computed values, but they are independent of each other and can run in parallel, providing scalable speedups. And finally, the last question is, how do we balance the workload fairly among all cores to get scalable speedups? So we use the idea of work stealing inspired by task parallel programming to balance the load among all cores. So with FP Sanitizer, we have inlined the high precision computations with floating point instructions as shown in red here. So we can compare both to compute the numerical error. And as inline shadow execution provides a fine-grained comparison of floating point instruction and high precision instruction. So this is great, but to reduce the overheads, our goal is to run shadow execution in parallel with the original program. To achieve that, what if I delete floating point instructions from the instrumented program and create a new program in higher precision automatically? Now, this idea enables us to run the high precision program in parallel with the original program. But this is not enough for two main reasons. First, we want to run the high precision program in lockstep with the original program to assist in debugging. And second, running a high precision program on one core won't give us speed up because high precision program is very slow. So the question is how we can execute a parallel shadow program in lockstep with the original program. To enable that, we instrument the original program to provide the floating point values to the high precision program through buffer. And this enables the execution of high precision program in parallel with the original program and yet provides the fine-grained comparison to assist in debugging. But it is important for the shadow task to follow the same control flow as the original program. Otherwise, our analysis won't be correct for the original program. And to enforce that, the original program also provides the branch conditions to the shadow program. Our compiler updates the branch instructions to use the branch conditions from the original program. Along with branch conditions, the original program also provides the memory addresses to propagate the metadata through memory. So shadow tasks map each memory address to the unique address in shadow memory. So this approach with one producer and one consumer can provide some parallelism, but the high precision version is so slow, it's not going to be faster than the inline shadow execution. So now the question is, how do we split the shadow execution into multiple shadow tasks to get scalable speedups? And this is where we rely on the user and ask the user to chop off various parts into multiple shadow tasks. If the user don't create a slice, then the entire program is one shadow task. And to explain that, let's consider a simple program that calls a function foo in a loop. So if the user wants to do shadow execution on every invocation of function foo in parallel, then user should create a pragma pfsan as shown in red. A compiler would generate a high precision shadow task, which is foo shadow function in this program. And there would be k shadow tasks at runtime if the loop of the function main would run k times. A runtime balances the load using a work stealing algorithm and executes the shadow task in parallel on multiple cores. So these shadow tasks are serial since we have created from a sequential program. And if we want to execute them in parallel, we need to break dependencies. And to break dependencies, we need to provide appropriate function arguments and memory state. So now let's see how do we break the dependencies between shadow tasks with an example. Suppose you have a program in which main function calls the function foo and bar. And as it can be seen, function bar accesses the memory which was written in function foo. Now the user might want to run shadow execution of function foo and bar in parallel. Hence, the user can mark the functions using pfsan pragma as shown in red. Our compiler would automatically generate the code in higher precision and instrument the original program and the shadow task to communicate via buffer at appropriate points. The shadow task map each memory address with a high precision value using a shadow memory. So each worker thread had its own shadow memory, which is located with the shadow memory of other threads. The shadow memory is organized as a hash map, and memory addresses are used to map the shadow memory. But shadow tasks are new programs, and they do not have the memory address of the original program for load and store instructions. So now let's see how we map the memory address to shadow memory in the shadow task. So in function foo, the program is storing a floating point value at address y. Our instrumentation provides address y from the original program to the shadow task. The shadow memory maps this address to the location where we have a real value corresponding to the FP value at address y. So in function bar, same memory location is read in variable z. And for each load instruction, our instrumentation provides the address y and value read from this address to the shadow task. Bar shadow would access the shadow memory associated with address y and load the metadata. But since this memory location was updated in the previous shadow task, that is foo shadow in this example, hence metadata is not available in bar shadow. That's why we need a mechanism to detect such scenarios. So on every memory access, we detect if value being accessed is produced by the previous shadow task, or it has been produced by the same shadow task itself. If it is produced by the previous task, then we need to break the dependency. To enable us to detect such scenarios in our metadata, we maintain the value produced by the original program and the real value. So if the value being accessed in the memory is produced by the prior shadow task, then metadata have the correct original FP value produced by the actual program. And hence we compare the stored original computed floating point value and the value produced by the original program. If they match, then we use a shadow value from the metadata. And if they do not match, then we reset the metadata with original computed value, which is the case in this example. So at this point, our metadata is updated and our shadow task can start executing correctly. Hence, we use FP computed values to reset the metadata to break the dependencies among shadow tasks. So now let me summarize the performance results with PFP sanitizer. So on average, we experience a slowdown of 7.4x with PFP sanitizer with 512 bits of precision over a baseline with no instrumentation. So in our experience, low overheads enabled effective debugging of numerical errors with long-running applications. So we have also evaluated the speed up of PFP sanitizer over inline shadow execution, that is FP sanitizer. And on average, PFP sanitizer resulted in almost 30x speed up over FP sanitizer with 64 cores. So before I conclude, let me discuss the related work. So there's a lot of cool work in the past to detect and debug such errors in floating point programs. Grind and FP debug are well-known tools based on inline shadow execution. Both of these tools are grind-based dynamic instrumentation tools. FP debug does not provide any debugging support. Grind generates the DAG of instructions similar to our approach, but one of the things we observed that grind maintains metadata proportional to the dynamic trace of the program, and hence it does not scale well with long-running applications. In contrast, we store a constant amount of metadata per memory location. We perform shadow execution in parallel to detect and debug numerical errors in floating point applications. So to conclude, my thesis research introduces multiple cute ideas to reduce the overheads of shadow analysis with high precision computations. Our techniques are an order of magnitude faster than the state of the art. Moreover, we provide clear and clean interfaces to debug numerical errors with debuggers such as GDB. And with that, I would like to thank you for your time and happy to take any questions.
Thank you, Sangeeta. That was great.
Thank you.
And okay, maybe I can start off with the first question, and while others start trickling in.
Sure.
So, from your talk, I was wondering. So you introduced two different types of sanitizers, right? The inline and the the shadow execution. So, are there cases where, like, are there certain cases that the shadow execution misses that are caught by the inline?
Yes. So parallel shadow analysis. So what we are doing is we are creating these mini shadow programs. And when there is a disconnect from one program to another, that's when where we are going to miss detecting the errors because we don't have the provenance at that point.
Right.
So, but in inline shadow execution, so the a key idea is that we depend on the user for this insight. So if user has this insight that, okay, I'm debugging in this region and I'm sure there is no error between these two code regions, then it's great. Otherwise, we are going to miss. On the other hand, inline shadow execution is like it's going to be serial and going to do shadow analysis for the entire program.
Right.
But with 150x overhead, you won't be able to. So if your program is running for 30 minutes, then you have to run FP sanitizer for days to get any analysis done.
Right.
So with parallel FP sanitizer, you can incrementally detect errors with a lot more speed up in comparison to inline shadow execution.
Right. So you depend on like user specified pragmas in the shadow execution case, right? So is there is there some way by which the compiler can detect some of the, hotspots, so to speak, and try to instrument those automatically, and um, in addition to the user specified, or instead of the user, yeah.
Right, right. So we have been thinking about it, and for the compiler to know about the numerical errors, the one way we could do is doing static analysis.
Mhm.
But we don't have right now. We don't have this infrastructure. But this is like something for the future work, which we are currently thinking about. And another idea which we are thinking about is take a program, run this program, and get some insights about the program, about the rounding error, and use those insights to do the shadow analysis in parallel. So basically you have to do inline shadow execution once for the entire program, and once you find these hot spots in your program, then you can use it and just analyze those code reasons. So advantage of this technique is that you will get a speed up, and you don't have to, because debugging requires to run your program multiple times. So it's not like just you have run one time and then you are done with it. So if your shadow analysis is taking a lot more slow down, it's your program is really slow down because of shadow analysis. So you can run it once and get this data and use this data to help the compiler for the next time to find these code regions or hotspots where your program is not correct
Right,
in
especially
context
like
of.
certain functions or something that are called often, and if those are the hotspots, then
Right, right,
running it once you can get a lot of benefits.
right.
All right, makes sense. Okay, so we have a question from Cindy here. Did you observe increased performance overhead on compile time to generate relevant metadata?
Compile time. So actually, recently I was debugging eigen library, which is I think C++ header library. And when I was compiling with my, I think compiling is already slow. And when I'm compiling with my parse, it was taking a lot more time because now they are like part of you might be writing a small program, but it is that a small program is having this entire library, and now your pass is going to instrument it. So that's where I felt that there is a slowdown, like huge slowdown. Other than that, with C programs, I haven't faced this problem because we compile small programs and not the entire library together. I hope that answers the question.
Cindy, did you have any follow-up?
I guess a follow-up question I have is there any like properties of C++ that like causes the like increased compile time as opposed to C, or is it just more that is it just because you're compiling more?
Yeah,
especially
so
for like header only.
yeah, so I do not know if there is some property. So what I realized with my experimentation is that the entire library was itself in my program, right? Because it's a header library, so it's included with my entire program. So I'm compiling this huge library every time when I'm compiling any program. So I feel, but there could be some other reasons, but this is what I realized. I mean, this was like my intuition,
Yeah,
but I'm
absolutely.
not.
Thank you.
Yeah, yeah.
So are there cases where you run out of memory and are not able to continue running the FP sanitizer because of the overhead in metadata, the memory needed to store the metadata?
So with all the benchmarks which we have tested, we haven't encountered such issues. So we have run like long running benchmarks with the spec. And the key insight which was helping us to do this or not running out of memory is because we are storing constant. So the size of metadata does not increase with dynamic trace of the program. It is proportional to the static trace of program. So if there are like 100 static instructions in the program, then our metadata would be factor of 100.
Okay.
So that's why we haven't encountered. But the prior tools we encountered this issue, and that's why we come up with this idea to have a constant and proportional to the static trace rather than dynamic trace.
Got it. Okay. All right. While more questions come in, I have some more questions here about Sangeeta's journey. Okay, so Sangeeta, can you tell us a little bit about how you started your journey into learning compilers and what your first compiler project was?
Sure. So uh, before coming to US for my PhD, I was working in India for Samsung Research and Development Center in Bangalore, and I used to design networking caching proxies based on network protocols. And I did not know anything about compilers or programming languages, so I applied to PhD programs and focusing on networking and security. So I got into UIC. And I was working there with Chris Canish, not officially because he was my academic advisor. He was not my research advisor. And due to certain personal events, I ended up applying again in East Coast. So at that point of time, I was dating this guy, and he was in Jersey City, and he suggested, why don't you apply again to if you get into better school here in East Coast, you can move here. Otherwise, I'll move there. I thought, okay, seems like a good idea to try because I don't have any official advisor till now. So applied and I got into Rutgers. And in Rutgers, I wanted to work with Vinod Ganpati, who was doing amazing work in networking and security. And so I came to Rutgers, and within 6 months, I broke up with this guy. And turns out that Vinod Ganpati, he moved to India. So, and that's when I started hunting for advisors, and I met everybody in my department. And that's when I encountered that Santosh is looking for PhD students. So I started working with him. I did an independent study because I did not know anything about this area, about compilers, or I just could not even comprehend his projects, which were there on his website. So, and then I started working with him, and the first project which I worked was my first, FP sanitizer. That was like the first experience I had with compilers. So yeah, that's so it was like I did not plan for it. It was all serendipity, and I'm happy that I ended up working in compilers.
Oh, that's awesome. It's it's always cool to hear about the transitions for me, especially starting off somewhere and then getting into compilers because that was my story too. And I constantly feel like an imposter in the compiler world. Yeah,
Exactly. I still feel. I mean, I haven't like done much in compiler. I just hacked it to use it for my projects. But yeah, but I totally love this field. So
yeah. I think after this work, you totally have the compiler creds. No
yeah.
imposter. Okay, cool. And so the other question is, were there what kind of challenges, like emotional, mental, technical, other challenges that came in that happened in the journey while your PhD journey, basically, when you decided to do your PhD program or during your PhD program, were there any such challenges, and how did you deal with that?
So my entire PhD journey was a challenge for me because I'm working with a top-notch guy in his field and I don't have any background, right? And now there is an expectation mismatch. So when you are expected to run, you are just crawling. So it was very challenging, but I learned slowly and at my pace. And this was like the challenge which I faced while working as a PhD student. Emotionally, it is a troll on every international PhD student to live away from family, and it is like sometimes you need that support which you cannot find because you are living so far away from your family and friends. So yeah, so that was the and then COVID came and that has even magnified all these challenges. So yeah, yeah, these are the kind of things which I didn't realize when I started my PhD journey. I did not like realize that it's going to be this difficult. But to junior students, I would say that in like investing in your PhD is great, but also invest in people, find your support group, and work with them and have fun with them rather than just working, because yeah, you have to find a balance. Yeah.
Yeah, in a way, it's good, that you don't know all the things that you need to learn, because, or that you don't know, because then you'd never get started, right?
Exactly, yeah.
So, can you elaborate a little more about, especially finding your support group that helped you, and also overcoming, certain technical gaps that might have been there, that you might have had without a compiler background? What were your go-to resources, and how did you find mentorship to help you along?
So mostly it was like taking courses, online courses. So initially I took some courses in programming languages, and um, I read papers, discussing papers with your teammates and your advisor, which has helped me a lot. Um, and what else? Yeah, so reading and discussing and taking courses, I think that was what has helped me to gain that background. But I still feel I'm still not there, because programming language is such a wide field and compilers is such, and there are so many amazing things still to learn. So I'm still learning and I'm still growing. So yeah. And I don't know what was the second part of your question. Support group, yeah. So how did I find my support group? So luckily my brother is here in United States, so he has been an amazing support for me. And so I try to connect with students in my department, and I've made some amazing friends. And going to conferences was like another major amazing thing which I loved about my PhD, and I'm like really missing it, is going to conferences and talking to people there and making friends. So some of the friends which I made during conferences, they are still my friends. So, and another yeah, internships. So I did 2 internships at Microsoft, and during that time I made amazing friends, and they are like amazing support right now, till now, for me. So that has helped me tremendously during my PhD. I mean, without that, I don't think so. Like I got that positive energy and boost of energy which I needed to get my projects, forward. So yeah.
Yeah, that's great. I mean, it's always the people element, right? I mean, there's all, especially now, like you have so many blogs and email groups and all that, but finally have getting that real people person community, and being able, who you can talk to, who you can discuss with, and also who you can be like vulnerable with, is
Exactly.
yeah, is can be a make or break to go on a certain path.
Exactly. So when I went for my internship, I was in this, that I'm struggling and I'm alone and I'm the only one who is struggling. But when I went there and met all these students, and they are all were there in similar state, and that has helped me to get my confidence and to go forward with it. It's fine. We can learn whatever gaps are there. Everybody's learning. Everybody's scared. So yeah.
Yeah, cool. All right. Cindy has another question here. How would you compare your journey to familiarizing yourself within the networking space as opposed to the compiler field? Do you find these fields, these specialities to be similar at all?
Um, Not really. I mean, the research. So I did not do any research in networking. So if I would have, if I whatever I have learned right now, and if I'll apply to networking domain, it will not take much time for me, because the principle of research is going to be same. You have to find a problem, you have to find what people have done in the past, and you have to incrementally, find a solution to solve that problem. But um, it was a totally different experience of working in networking and in compilers. So yeah, you have to think from a different perspective, and it required to it's not just building systems. It requires you to learn some basic programming languages concepts. So for the initial of my PhD, I could not understand the difference between static and dynamic. So that has, so in networking, I did not have these challenges because I don't have to think about all these things. So it is mostly about building systems, and yeah, so I think it was totally different experience.
Yeah, just to elaborate on your point, right? I found that too, because it's like you're using the language, like like in most other programming tasks, it feels like you know a language, you're expressing an idea, and then you're trying to understand that idea. But when it in compilers, you're trying to understand the language itself.
Itself, exactly, and that requires some mathematical principles to understand that.
Yeah, and a mind shift change about how you think about things, because what your input is the program itself and not the input to the program. You know what I
Right,
mean?
right,
Yeah, it
right, right, exactly. Yeah,
makes it. Uh, I mean, that's one part which
yeah.
I had to wrap my head around when I made. Okay,
Exactly, yeah.
so we have some questions here, specific about your PhD journey. If you could give us some insight about, the struggle with writing research papers, and, what would you like to share some tips on choosing the right research topic, and then how do you go about writing research papers and, getting them accepted?
So writing is still something I'm still struggling with. So writing takes me more time than coming up with the idea and building the system. So and expressing that idea and in a coherent manner, it takes a huge effort, and I'm still struggling with it. So the kind of thing which I'm doing to improve writing is I did again. I took some courses in Coursera. So there's a writing specialization course. It has like 4 parts to it. I went through it to get the basic, and now I'm doing is I'm writing a lot. So to, so the only way you can learn writing is by writing. So, so sometimes it's like really hard to even get started with it. So now I just go and start writing whatever comes to my mind. I don't think about whether it's coherent or not. I'm trying to explain. So I just go on writing it. And once I'm done and I read it multiple times, and then I restructure it again. So it requires multiple iterations. And another thing which I started doing recently is taking feedback. So when I'm writing, I take feedback from my friends, I take feedback from my advisor. I involve many people to get their perspective into it. So yeah, these are the things which are which I'm learning till now. And okay, so there was a second part of this question.
Right, about how did you go about selecting your topic for
So yeah, so selecting topic. For me, I learned by doing. So when I started my PhD, I started with a project which is called as race detection in parallel programs. I started with it. I came up with some idea, I built it, but I was not getting the right performance out of it. So I failed. So it was like 8 months project, and then I picked up another. So these all problems are new for me. So I don't know. I haven't captured the taste of the problem yet. So for me, it is like I'm trying, I'm learning, I'm seeing, what is working for me and what is not. And then I picked on next problem, which was program synthesis and improving the program search space with machine learning. And I spent 7 to 8 months with this problem, and I failed again. And then came floating point, and I was like very fascinated by floating point. I'm like amazed with this representation. So every day I feel that I'm done. I know what floating point is, and next day I will learn something new about it, and it's like ongoing process till now. And I totally was hooked up on it. And I remember saying to my advisor that this is what I want my thesis to be on, because I felt connected. And yeah, so I started working on it. I failed. I've took 2 years to build FP sanitizer, but I kept trying this time. I didn't give up and moved on to the next problem. I just kept trying, and eventually it worked. So that was the whole process. But for different people, it works differently. For me, it is like I want to try it and see it and feel it and then decide.
Yeah, that's awesome, right? Yeah. Uh, Talking about floating point, have you ever read that what every computer scientist should know about floating point?
That was my first
Starting point.
thing, starting point. And I had to explain it to my entire lab. And I still remember Santosh yelling at me because I couldn't get the sign bit correct. So this was like the first thing which I, learned. That's how I started learning floating point.
Right. That's a like a monster paper, right? It's like
Yeah,
big.
yeah,
It's not like a two-page
yeah.
document or
It's
something.
like 10, 20 pages or something. Yeah, yeah.
Cool. Right. So my last question to you, let's see if you have any other questions. Okay. Uh, is do you participate in any open source projects and how your experience so far has been? And do you have any advice for newbies in the open source community who struggle to ask questions or push their pull requests and some, pointers?
So open source projects I have worked with is with team collaboration. So I worked with EVA team at Microsoft, and this is an open source project. So I did internship. I built some infrastructure of this compiler, and that's how it got pushed into EVA. But I'm not sure about how like out of if I'm out of loop and how I'm contributing that project, that I'm not sure about, and I don't know struggles related to that because I haven't tried anything like that. So mostly my projects are I got involved and then I contributed towards them.
So is the FP sanitizer a part of the LLVM code base, or
Infrastructure, no, it is not. It is not, but it is open source. I thought you were going to ask, is FP sanitizer?
I sent your GitHub link to it.
Yeah. So it is open source. Both of my tools are open source. Yeah.
Okay.
But it's not part of LLVM and infrastructure yet.
Okay. Is there a plan to get it there?
I think we started this discussion, but I'm not sure how to, I'm not sure if there has been any progress on it. But yeah, we started this discussion to, get it. I think I talked to someone in LLVM, community when, so I submitted my work for a talk in LLVM community, but I'm not able to recall right now. So, whether it has been, so something we started, but it didn't go anywhere. So maybe that's something, to think about going in future.
Okay, cool. All right. So opening up the floor, does anybody have any other questions for Sangeeta here? Comments?
Hey, Sangeeta.
Hey.
Nice. Yeah, I think I missed some part of your talk, but I know quite a lot about your work, and it's really great. So thank you so much for contributing in the floating point domain. Not many people do that. So you're doing such an awesome work, and it's very complicated. So you've taken a big challenge.
Thank you so much, Julie.
Yeah, and I do resonate with all the feelings about writing, about rejections, about failures. So don't worry, that's how I think everyone does. And you're just there. So, kudos to you for sticking in and finishing it.
Thank you so much, Julie. Thanks a lot.
Yeah, and thank you so much for, keeping it so real and, giving answer, not the, what do you call it, like canned answers, but, the real answers about the struggle and about, the various aspects of fitting in and learning and all that.
Sure.
That's my favorite part about the Meetup group that I have, and I'm so glad that we have speakers like you who come and tell us the real story, and so we know that it's not that somebody just had it easy and then we'll never get there because we don't have it easy, but that there is the struggle along the way. All right. I think if there are no questions, we can call it a night. Do you have anything else?
Thank you so much for it. It was amazing. Thank you so much for providing this opportunity and letting me share my work.
Yeah, absolutely. And thank you so much to you. I definitely learned something about floating point numbers and programs that use them. Thanks everybody. Hope to have more speakers and more interesting talks as the new year rolls in.
Yeah, looking forward to more getting involved. So so this is like right now it's 10 p.m. here. So usually I go to bed by 9 p.m. But but I totally loved I always wanted, so I always sign up and register RSVP, but then eventually I'm not able to, but I definitely try to join and get involved and haven't listen to other speakers talking about their work.
Thank you for, and sorry for keeping you up so late.
No, that's totally fine. That's totally fine. I was just mentioning it so that I can get an excuse why I'm not attending. That's why. Otherwise, it's totally cool.
All right then, everybody.
All right.
Happy
Bye-bye.
holidays. Wish you all
Happy holidays.
happy New